Welcome to the Sabre RD online training course. This series of fast-paced videos will teach you the full power of the Sabre RD simulation environment. In this section, we explore worst-case analysis. Will my design always work, even in extreme conditions? Sabre's worst-case analysis answers this question. It identifies combinations of component parameters and operating conditions that diminish performance. Addressing these worst-case corners creates a robust design. Traditionally, there have been two approaches to worst-case analysis. One of them is extreme value analysis. This method simulates the design multiple times, using only the values at the extreme ends of the parameter ranges. Unfortunately, this method falls short in many instances where worst case occurs with some parameters not at their extreme values. Another method applies random Monte Carlo runs, after which it identifies the run with the worst outcome. More random attempts will give one a better answer, but it's difficult to determine how many runs are necessary for a high level of confidence in the result. Sabre's worst-case analysis examines the complete range of parameter variations while methodically searching the entire solution space. It determines the precise set of parameters that gives us the true worst-case conditions. We can think of Sabre's worst-case analysis as the opposite of design optimization. Optimization finds the set of parameters that maximize performance. Worst case determines the parameters that minimize performance. In Sabre, one tool performs both analyses. Let's look at Sabre's worst-case analysis process. It begins with a design using a nominal parameter set. It simulates the design and performs measurements on target waveforms. These are the baseline results. A search algorithm modifies the parameters and executes the loop again. Looping continues, perhaps hundreds of times, to find the set of parameters that meets the objective. Let's go through an example. Here is an AC to DC switching power supply. The worst-case condition we want to determine is the longest settling time upon power-up. We find worst-case analysis under the Analyze tab. Pressing the Edit Parameters button lets us select which ones to alter during the analysis. The first one we choose is the amplitude of the input AC voltage. We find it in the parameter tree, double-click to select it, and specify the lower and upper limits. This is the range of values the search algorithm will consider. The other parameters we want to include are the resistors, capacitors, inductor, and reference voltage. Instead of manually adding them to the list, an easier way is to have distributions defined in the schematic. The first term of the normal distribution function is the nominal value, and the second one is a tolerance. In this example, the nominal value is 4.7 K with a 1% tolerance. This means the search algorithm will consider values between 4.65 K and 4.75 K. We can use the uniform distribution function in the same manner. With the parameters of interest defined with distribution functions, we use them to generate the parameter list using the extract stochastic parameters function. We extract the parameters and append them to the list. Note that we don't use the distribution functions in the worst-case analysis. Instead, the values are converted to hard limits, which we can manually edit. Now we define analyses. The first is a DC analysis, followed by a transient analysis with a time end of 10 milliseconds and a time step of 1 microsecond. Next, we define a measure. We give it the name settle time. The target waveform is DC out. We choose settle time from the time domain submenu. The settle band defines the maximum deviation when the waveform is considered settled. We set it to 0.5%. Now for the objective. Since we are looking for the worst-case settle time of the output voltage, we specify max of the settle time measure. We leave the search algorithm set to the 3 defaults. It's time to run the worst-case analysis by clicking the gear icon. The algorithm evaluates different parameter combinations. Within the Signal tab, we can see in real time how the DC out signal changes with each iteration. Selecting the Progress tab, choosing the settle time measure, and zooming to fit shows how it increases as the algorithm works through different parameter combinations. We can also monitor parameter value changes during the analysis. The search continues until it completes all the iterations for the 3 algorithms. This gives us a set of parameters which causes the maximum settling time. With the worst-case analysis complete, we need to save the parameter set. From the File menu, we choose Export, Parameters. The choices include creating a new schematic with these parameters, temporarily changing the parameters during the simulation session, or creating a tab-separated text file for import into another application such as a spreadsheet. An integral part of SABRE's worst-case analysis is the search algorithm. The SABRE worst-case search algorithm follows the contours of the solution space to find the absolute worst-case solution. A combination of search methods avoids local minima while converging upon the answer. We can choose from a wide range of search methods. Each is described in the SABRE user manual. For most cases, the default set of algorithms are the best choice. Running the analysis multiple times, starting with the previous solution, can sometimes produce a more extreme worst case. This can be automated by increasing the number of algorithm sequence loops. If a particular method doesn't seem to be effective, uncheck it to keep it from executing. We can start and stop the search as we wish. While stopped, we can manually change the parameters. Checking the fixed box holds a parameter value. SABRE's worst-case analysis finds the most extreme conditions of circuit performance. Even though it may be unlikely these circumstances occur, we gain valuable insights into conditions where performance degrades. Keeping our design within reliable regions of operation makes for a robust design. This concludes this section of the SABRE RD online training course. To download a free student version of SABRE RD, go to the Synopsys website. To further your understanding of this material, go through the lab exercises found at the link listed in the description of this video.